Well, guess what? This is organic chemistry. Of course there's a carbon in the molecule. As you work your way through spectroscopy land, you've almost certainly encountered a question like this. A full page, here's all the spectra, the IR, the NMR, and the mass spec. Go. Solve the structure. Do what you need to do to solve the structure. And maybe when you do that, you spend a lot of time trying to extract as much information as you can from something like the IR and something like the mass spec. I'm here to tell you, you should not do it that way. You should only spend at most 30 seconds on mass spec. I also think you should only spend about 30 seconds on IR, but I've got a separate video on that down below. What do I mean you should only spend 30 seconds on mass spec? Isn't there so much information in there? Yes, but not all of it is diagnostically useful. In this video, I want to take you through what's diagnostically useful in mass spec and what you can pick out in 30 seconds before you can move on and spend most of your time on the NMR, where the real information lies. As you first learned mass spec, you probably looked at a spectrum somewhat like hexane, maybe even hexane itself. And we probably use that spectrum to teach you a lot about the nuances of how a mass spec works and some of the things you can see when you look at a mass spec. I'm going to go through those again briefly, and I'm going to separate them into two categories: diagnostically useful information and not diagnostically useful information. Some of these may seem like a surprise to you, but I'll explain as we go along. The first thing I'd like to say, when you look at hexane, the one thing that you do want to look at is the M+ peak. The M+ peak tells you the molecular mass of the molecule. It's a good confirmation when you're all done that you've drawn the right molecule. It has to add up to the right molecular mass. If you are not given a molecular formula, the M+ peak is also useful for finding a couple of possible molecular formulas using something called the rule of 13s. If you don't know what the rule of 13s is, it's a really cool rule, and I've got a separate video on the rule of 13s that I'll link to down below. So the M+ peak really is a useful piece of information in mass spec. After that, you may have learned some nuances, like there's a small peak just above the M+ peak, 1 mass unit above. That peak arises from any molecules that have a carbon-13 element in there. You may have even learned something about the ratios of those and how you can use those to find the molecular formula. I think the rule of 13s is better for that. I don't think the M+1 peak is very diagnostically useful. What does the M+1 peak tell us? It tells us there's a carbon in our molecule. Well, guess what? This is organic chemistry. Of course there's a carbon in the molecule. That's not diagnostically useful. All the M+1 peak should really do is give you a little bit of a warm fuzzy in your heart that yes, you are still an organic chemist, and then you should move on. After that, you may have learned that there's an M-1 peak, and in fact, if you look at each cluster, they all kind of tail off a little bit to the left as you get successive M-1 peaks. That results from the loss of a hydrogen atom from the molecule. Again, this is not very diagnostically useful. What does an M+1 peak tell us? It tells us there's a hydrogen in the molecule. Guess what? We're still organic chemists. There's still going to be hydrogen in the molecule. This is not diagnostically useful. Don't waste your time looking for M-1 peaks. After that, you might have learned about the M-15 peak for the loss of a methyl group. Now, I can hear what you're saying. Surely the loss of a methyl group must be diagnostically useful. I'm going to say that it's not. By the time it takes you to figure out if there's an M-15 peak, do the math to confirm that it really is M-15 to figure out there's a methyl group. Guess what? The NMR is going to tell you if there's a methyl group. If there's a methyl group, you're going to figure it out from the NMR. You don't need to go digging in the mass spec to do all this math to figure out there's a methyl group in the molecule. The NMR will do that for you. The M-15 peak is interesting, but it's not diagnostically useful, and I would not waste my time looking for M-15 peaks. Finally, from this, we get an M-29 peak. M-29 peak is indicative of an ethyl group fragmenting off the molecule. Surely, again, that must be useful. I don't think so. Again, if there's an ethyl group in the molecule, you're going to figure it out from the NMR. The only reason I would ever go digging for an M-15 or an M-29 peak is if I'm really, really stuck and I just really don't have any leads. Then I might circle back to the mass spec and look for an M-15 or an M-29. Otherwise, we're going to figure it out from the other spectrum. If we look at this other example mass spec, we can see one other reason why the M+ peak is useful in mass spec. If the M+ peak is odd, that's indicative of an odd number of nitrogens in the molecule. I have a video explaining why that is down below, but if we see an odd M+ peak, then that tells us there's an odd number of nitrogens in the molecule. That is very diagnostically useful. Two other quick places where the M+ peak is diagnostically useful is if we have an M and an M+2 peak in our M+ region. That's indicative of some kind of halogen, bromine, or chlorine. If the two peaks have a 1-to-1 ratio, that's indicative of bromine, and if the two peaks have a 3-to-1 ratio, that's indicative of chlorine. This is very diagnostically useful, and you should definitely look at the M+ region to see if there's a bromine or a chlorine in the molecule. As you move through the mass spec unit, I'm willing to bet you spend a lot of time looking for M-18 peaks in molecules containing alcohols. That covers the dehydration fragmentation. Certainly that must be useful, knowing there's an alcohol in the molecule. Again, I'm here to tell you I don't think it's that diagnostically useful. I would not spend a lot of time hunting for M-18 peaks in the molecule. For one thing, if you have an M-18 peak, the M+ peak might be so small that it might not even be visible. So you might not even be able to see the original M+ peak to know there's an M-18 peak. Second, if you've gotten through the IR unit yet, you're going to know if there's an alcohol. The IR unit screams if there's an alcohol in there. So we don't need to search the mass spec to figure out if there's an alcohol. The IR will tell us if there's an alcohol. There are two other things that I would recommend looking out for that are diagnostic in mass spec. And these are peaks at certain mass units, not loss fragmentation, but at certain mass units, at 43 and at 91. If I have a peak at 43, that's often indicative of a methylcarbonyl fragment in the molecule. Knowing that I have a methylcarbonyl fragment is very indicative, is very diagnostically useful. The last peak is at 91. At 91 mass units is indicative of the tropylium ion. That's an unsubstituted benzene ring with a CH2 group sticking off of the benzene ring. Got to be that substructure. Got to be otherwise unsubstituted with just a CH2 group sticking off of the benzene ring. Anything else would not count for the tropylium ion. But knowing that we have a tropylium ion or the methylcarbonyl that we call the acylium ion, that is very diagnostically useful in organic chemistry. So an approach with the new unknown mass spec, I'm not going to spend too much time on there. First thing I would do is I would note the M plus peak so I can come back to it later. In this one, I note that the M plus peak is at 212 and 214. The 1-to-1 ratio says that there's going to be a bromine in the molecule. And I look through the fragmentations, I see the at 91 stick out to me. So there's going to be a benzene ring with a CH2 group attached to the molecule. This is what I get from the mass spec, and I'm going to move on. I'm not really going to go looking for anything else. I don't see a 43, I don't see a chlorine, I don't see a nitrogen. Might even be useful to write those down if you want to. So no chlorine, no nitrogen, and no methylcarbonyl. So those might be useful to write down as well, but I'm really not going to spend much more than 30 seconds on this mass spec, and then I'm going to move on to the IR and the NMR. But just in those 30 seconds, I've actually gotten a lot of information. My final structure needs to have a bromine. My final structure is probably going to have one of these benzene rings in it. My final structure had better add up to 212 mass units, and I shouldn't have a chlorine or a nitrogen, and I probably won't have the methylcarbonyl. That's a lot of information in just 30 seconds. As I look at this next unknown, I'm just going to jot down what I see. What I see is that the mass peak looks like it's at about 120 and 122. And the 3-to-1 ratio tells me there's going to be a chlorine in the molecule, and I see this very prominent at 43 peak indicative of the methylcarbonyl. So I expect those substructures of my molecule. I don't see any evidence of a bromine. I don't see any evidence of an at 91 tropylium ion, and I don't see any evidence of a nitrogen. So I would not expect those things in my molecule. Time to move on to the IR and the NMR. With this last unknown, really all I see is that the mass peak is at about 101, so that's indicative of a nitrogen in the molecule, but I don't see any evidence of bromine or chlorine or at 91 or at 43. I would not expect a tropylium or an acylium ion or any bromines or chlorines in the molecules. This is going to be just a molecule that has a nitrogen and whatever other functional groups I see in the IR and the NMR. So that brings us around full circle. That's really all the time you should spend on mass spec. Check for the M plus peak, do a rule of 13s if you need to, look for nitrogen, bromine, or chlorine, look for the at 43, look for the at 91, jot those things down, and then move on. That's it. That's all I want you to spend time on. Move on to the IR, then spend most of your time on the NMR. That's how you can spend 30 seconds on mass spec and really extract a lot of information from that one spectrum.
I'm glad you're here with us for this training today. Check out these other videos in my playlists to see if there's anything else that can help you level up your ninja levels even further. As always, don't forget to like and subscribe.